So, all right, let's get started. On Thursday, I plan on going over the next topic, which is going to be dictionaries, which are extremely powerful data structures that you'll learn in more detail how they work in 2168, but they're extremely powerful. Simply put, they are essentially lists, but the indexes can be whatever the heck you want them to be. They can be numbers, they can be words, they can be other weird things, whatever you want. Makes them very flexible, but we'll go over why that's important later. By the way, just to kind of just give an overview of where we are. So this week, I plan on going over the Hawaiian pronunciation. Not sure why that has these each have a due date of 2 weeks from now. Oh, sorry, of doing 2 weeks each. Although I haven't tried that before. I might. Why not? But I do need to adjust these because the progress. Wait, no, we're good. Yeah, I might try that. Who knows? Might give them a bit of flex between these assignments because students do tend to find these assignments to be a bit more difficult. Although once we start with Hurricane Tracker, we're on a trend of assignments appear to be more difficult than they actually are once you understand how they work. And once you understand how they work, you're like, how could I not have seen this before? Which is unfortunate because that makes you feel silly, and that shouldn't be the case. But our topics are, we're going to go over dictionaries, and we're going to finish up file reading. We're going to go over dictionaries, and then I'm going to go over Monte Carlo approximations, and that's it. Believe it or not, you're almost done with the curriculum. I know, that seems weird because there's still like 5 weeks left. What happens after that? What happens after that is that I start going over various topics that are, how to say, you may or may not need depending on what your future looks like. If you're going into, one of the things I'll be going over is regular expressions. Regular expressions are something I lecture on. I used to make them a mandatory part of the class, and I still have that content on the final. But on the final, you get to, again, choose. There's going to be a number of questions, and you get to choose a subset. So if you don't want to if you don't want to spend the time to learn regular expressions, then you just don't choose that question on the final. But if you do choose it, suddenly you get like a really easy, 16 to 20 points on it, because that's it's a very straightforward kind of deal with that. I will also go over different ideas for the final projects. I'll be going over different kind of use cases. I'll be going over maybe some projects from the textbook at the end that for more interesting to just I try to make it appeal to just about everybody. Another thing and depending on how much help is needed on these assignments, I'll be going, I generally do like the first 4 parts of Pig. Pig is an 8-part assignment, which sounds terrifying, but it's not really. They're broken up into those steps to make it good and nice and easy to do. Oh yeah, in Module 10 we do go over GitHub. GitHub is kind of the de facto place that you make a portfolio as a programmer, to basically say, this is my work. It also serves as a kind of ultimate defense against the laptop just died and I lost everything, all my work kind of thing. It's that, but on steroids. It allows for it's a platform that allows for a large team-based collaboration for a lot of people to work on the same files, a lot of different versions on the same files, and to give you tools to merge them together. It's actually quite powerful, and it's one of the main tools that is used. It's really nice. And as we get closer, I will go over like what we do in terms of these modules. In terms of the final project ideas. So with regards to, the emails I sent yesterday, I'm happy to report that nobody automatically failed the class. Hopefully you read the email with the multiple warnings saying, please don't send me the phrase about not knowing you have to demo the assignments, because that triggers an automatic fail. I did have to send a email to a student last semester suggesting to them that perhaps they had accidentally sent a draft of an email and had forgotten to proofread it, and maybe email me back when they fully proofread their draft. And hoped that he would get the hint. But but the reason being is that I generally want to make sure that you know that you have to demo your assignments. If you have not demoed your assignments, please do so in lab or find time with your TA to do so if you've just been neglecting to do that. If you've gotten the work in, great. It's generally at the end of the semester where we go, no, that's terrible. We don't want to do that. Similarly, if you still have to turn stuff in, I would do so. There is a late penalty, but we're generous about it. The Runestone stuff, right? If as you saw in the email, once you do it, I'll run the grade. At some point, if you've done it, I'll run the grader again at some point. Okay, so grade. You just work on it, catch up on the work. At some unknown point in the future, I'll run the grader on all the previous assignments, and then that will be what updates the score. Okay, and then then I will run my import script. Now, this is my import script. Believe it or not, this is what I use to do a lot of my work for me, to copy over your grades from Runestone into Canvas. And what I have to do is that I download the grade book from Canvas as a CSV file, okay, a comma separated value file. And I download the grades from Runestone as a CSV file. But unfortunately, it's not a matter of just simply being able to copy one and put it next to each other, because Canvas updates regularly to discard students who have signed up, who have withdrawn from the class. So those rows get deleted. Also, sometimes students make a mistake and they make 2 accounts on Runestone, which can lead to all sorts of stuff. Or students, and that can just be, or sometimes they just neglect that they need a Runestone account. And I looked at that and I'm like, I don't want to have to copy everything over, one at a time, and I don't want to just have to kind of eyeball it like I did during COVID, to be honest. I eyeballed it for one semester during COVID. I'm like, this is not a feasible solution. I'm just going to go ahead. It was worth less points then. It was doing the textbook assignments was only 5% of the grade, and that included the solo exercises. But I wanted to add in this to be more of a component to that grade. So what I did is that I created this script. And this script is what it does. It relies off of 2 files, Canvas CSV, Runestone CSV. So, and then over here you see output.csv with a W command. So we see this open W command, and then that is output. And that just simply tells it how to open. So the first thing I do is I have I have import CSV, which is a library for reading CSV files. Not really important to know too much on how that works, other than it just simply helps me do that. Runehash and Rune emails. So let's see what that does. Runehash says, okay, so what Runehash does is says, basically this is the dictionary I created. Rather than using an index and then setting a value to it, like 0 apple, 1 banana, 2 carrot, okay? Rather than doing that, what this does is that it sets the index to be whatever the heck I want it to be. In this case, your name. So for me, it would be Andrew Rosen as the index. So what's the value? What gets stored in it? A list of your grades. That's what gets stored in it. So it's a way for me. So it's a key value mapping. It's the same kind of thing of how when you log into, your Amazon account, if you have one, it knows what's in your cart, because your key is your email address, your account, and the value is basically all that information that's stored on Amazon. Rune emails allows me is one step, and what that does is that it helps me later on if I need it. What that does is says, given an email, give me your name. Okay, that's what it does. So what I simply do is I say, hey, okay, give me read the email, read the grade book, and then turn each line into a list. That's what this does. The with open is just a fancy way to do, this is kind of just a fancy way to do this, by the way. Okay, so give me a second. I could have alternatively just done this, but I was playing around with the with statement. You can look it up in your textbook. It's a safer way to open stuff. And the safer, that means that it's more polite for the system. So I could have so this is the same exact as me going open runestone is equal to open runestone.csv. The difference is that it knows is that once this with block is done with, it knows that, oh, you're done with that file. We can close it now. Make sense? So it automatically handles that closing. So that's all that is. Okay. So I get this, and then I say for row in rune 2 to the end. I believe those first two rows are just not things I care about from Runestone. And then I just basically, what I do is I grab what your name is. I grab the name, I capitalize it. So capitalize is different than upper and lower. Upper turns everything into uppercase, all uppercase all the time. Lower turns everything to lowercase for a string. Capitalize takes a string and does what you would expect it to do for a name, which is first letter is capitalized and then the rest is lowercase, right? Okay. And then I get your first name and then your last name. And then your email address for when you signed up, and then the rest of your grades get stored. So I just simply store that all into the dictionary so I can use it. Okay. Now, what do I do with that? I open up the CSV file. I create a CSV file to write everything out to, and then I open up the Canvas gradebook. And what I do is I say, for every row in Canvas, what I need to do is I'm going to look at the name, and I'm going to grab your name from Canvas and your email from Canvas. If your name is an exact match, awesome. I found you. I can get all of your data plus all the data and I just simply stick all the stuff from Runestone onto the end of that row. So I just simply extend your row. I glue it all together. If I can't find your name, then I check your email that you signed up with, right? This is why I told you to sign up with your name that matches in Canvas, and if not, your Temple email. If not, I look for your email. Otherwise, I try doing stuff like I try removing your middle initial. There's probably other stuff I could do. Otherwise, I just continue on and just leave it blank, essentially. And that's it. And that's how I kind of grade it together. So it took me about 20 minutes to write this script. Back when I started, when I changed the syllabus over to make it, to do the solo exercises and the in-class exercise. It took me about 20 minutes. It saves me about, I'd estimate, at least an hour of work if that was all I was doing. If I'm going to be honest, when it's tedious, I'll probably put on some anime while I do it, and that would take about 3 hours because everybody knows that you work not really as good when you're distracted. So it saves me quite a bit of work because all I have to do is run this script, and it takes 10 seconds to run, if that. And then I upload it to the file. The main things that can go wrong with this, though, the one thing that can go wrong, though, is that you may have done the work, but I wasn't able to detect you, right? So if you received a bunch of zeros or don't have any grades for your Runestone stuff, it's because I didn't detect you. And that's fixable. Just let me know about it, right? Because manually copying over one person's Canvas information, or 2 or 3, which is generally how many exceptions we have a semester, is a lot easier than doing 250 people's worth, right? So that's the entire point of that. So if you have a bunch of zeros and you did the work, or you have a bunch of blanks and you did the work, let me know, and I'll make sure to fix that, okay? Make sense to everybody? So, again, if you ended up with a bunch of zeros, yeah, so did a lot of other people. Don't freak out about it. Just get it done, right? By the end of the semester, and it will get fixed, right? So that's number one. Number two, you probably saw my email that with the satisfactory, unsatisfactory, because there is no penalty to you for me sending you an unsatisfactory notice. I get very aggressive about sending them out. They might simply be as simple as saying unsatisfactory because you're below a 70 in the course, unsatisfactory because you're missing all your runestone assignments, so you're like a letter grade lower than you should be, right? Or a unsatisfactory of a, in the case of an unfortunate number of cases of, you haven't turned in anything, and you haven't done any homework, and I don't think you took the exam. Could you, just, you're still in this class. You might want to not be in this class anymore, kind of thing. It's like, you get 6 withdrawals. Most people don't use them. So, just trying to make sure that I alert students that there's an issue going on here. All right. Any questions about the undergrad reports or the midterm reports or turning stuff in? Right? I had not had the opportunity to check what the average is on the exam. Generally, though, it is around the C average for the exam. So, and again, the way I've set this course up is that the assignments and the assignments in the final project make up 50% of the grade, which provides a rather high buffer for it, because you should be able to get 100% on all the lab assignments, 90% on the final project, and close to 90% on the, if not 100, on all the solo exercises and runestone exercises. Assuming you do them all, maybe you miss a couple, right? So, long story short, you can do that. I've had a number of cases where students would have passed the class had they done the runestone assignment. So, that's my freebie for you. Similarly, the in-class assignments, that's essentially the participation grade. A lot of those in a lot of cases, you just simply get credit for putting something in, including a print statement. So, it's, just make some amount of effort. Okay. Okay. So, Hurricane Tracker is a couple of emails I got about Hurricane Tracker, by the way. So to write the numbers on the screen for the turtle, right? Part of that is to print so part of the Hurricane Tracker. Let me just pull up the video again for everybody so that we're all on the same page. Part of that is to do this, right? And let me go ahead and turn up the resolution on this. Okay, part of this, as you can see, as this guy is going, he's printing out the category of the hurricane, right? So that's part of what you have to do. Now, some of you maybe are like, well, I'm having trouble. Some of you have sent me emails or Discord messages along the premises of, I'm having trouble with this. It's writing, but the line is overwriting what I'm writing. That's okay. Okay? I'm happy that it's just writing out. There are arguments you can give to make to change how it works. Worst case scenario, you can always add a tab in front of what you're printing out, or a couple spaces in front of what you're printing out, and then increase the size of what you're printing out, the font size. So, but if it's printing, then you'll get credit for it, right? Even in this one, you can see it's kind of overlapping the graphic. The thickness of the line is making it overlap the fives. So, even in our demo solution, it's fine. Okay, we just want you to, to know turtle.write. How are you supposed to know about that? By going to the turtle documentation, right? So where is that? Well, docs, turtle. Turtle graphics, Python 3.13. And this has every function built into Turtle. And you're like, okay, I want to print something on the screen. Print. No, that's about printing, and I'm just doing Control F to find stuff. No, okay, I want to, or maybe I want to write it onto the screen. And if you look, oh, there's a turtle.write method that I found just simply by doing that. Okay. And turtle.write. Right, and you can also find it just by simply looking at the top, where it mentioned, where it just has all, these are all the methods that Turtle can do. And write, what that will do is that it will write something, move, true or false, align, how is it, what's the alignment for it? Is it going to be right justified, left justified, or center justified? And then what font are you going to use? Okay, and then it's got some examples there. Okay, can we run those? No, okay, that's just simply giving me those things. Interesting. All right. So there's ways to, so that's how you handle that writing. All right. Any questions on the Hurricane Tracker before I move on? Very quiet class today. All right. So, also, my last piece of advice for if you've been trying to run this in, having trouble running this in VS Code, when you go to run, I would try run without debugging, which is different than the run button you have over here. Run without debugging will basically just run it where it is, rather than using a and you can basically, if you don't do that, you're going to have the project folder opened so that it will know where all the files are. But if you just run it without debugging, it will kind of run it like a Python, like a regular script, like you were doing it in idle. At least that's what it appears to be for me. All right. So let's see. So module 8. Then we go over here onto Tuesday, which is the common words in SETI that we were talking about last class. Now, last class, in case you remember or don't remember, in case you don't remember, we have this data. We have this data here, 5,000 words that have just been. We have like billions of documents or millions of documents. And it just simply ran a word count on every single one of those words, basically asking how often these words appear. Frequency is how often the word appears, and dispersion is a measure of whether or not that's a word common in every area or just common in a very specialized area. All right, and we did the very first part, I think, which was, because we had other stuff going on, which is just simply we have a list for the rank, the word, the part of speech, the frequency, and the dispersion. Basically, we have a list that represents each column. And index 0 represents one of the rows, index 1 is one of the other rows, index 2 is another one of the rows. And so what we did is that we read all the lines, we chopped off the first line because that first line has the legend telling us what's going on here. And then we said for every line in the file, split up the line into multiple parts, right? Split it by the commas. So it will end up being something that looks like this, which is the rank, some rank like 7 or 8. And then it has the, whatever the word is, let's say B, and then it has a part of speech, which was I think it was infinitive for this one. Regardless, you get the idea. No, not infinitive, that's just verb. 2 is the infinitive. And then, there we go. So, now what we're going to do today is we're going to explore a phenomena called Zipf's law, which is, it does look like somebody kind of mashed on the keyboard for that name. But it's a real law. It's a Zipf's law. Basically, is saying that when we have measured values in decreasing order, it says the value of the nth entry is often approximately inverse proportional to n. What that means is that, at least in our context in languages, what does that mean? It means that if we were to list all the words by how common they are, like we do over here, that each of these words, we can kind of expect almost a decrease and almost halving between each rank or series of ranks. So look over here, 220 million for our most common word, the. The next most common word, which is B, has 125 million entries. That's half. And then we see 107, 103, 101. We can kind of consider this a cluster of 120 to 120-ish, right? These are kind of clustered around the same frequency. Then the next one after that, we see another huge decrease to 70 million, from 120 million to 70 million. And then we see from 70 million to 40 million. And then we see from 40 million, right, to around 30 million, to 35, and then from 35 to 30. And so it goes down, it starts going down fairly rapidly. What this is saying is that words that appear in language often appear in languages really freaking often. Okay? So, for example, the Brown corpus of the English text, the word the is the most frequently occurring word, accounting for nearly 7% of all words, okay, that they counted. And then the second place, of, occurs around 3.5, accounts for about 3.5% of the words. Okay? So what's fascinating about this, okay, with Zipf's law, is that it is a hard thing for communication. It's like a hard rule of communication. Okay? Like, we see it for all sorts of languages. Let me see over here. Like, let's see. We have that here. I want to make sure I'm not spouting gibberish so I always try to find wherever I found it previously. But this is a hard law for basically pretty much a bunch of languages, but also like any kind of communication that happens with creatures. So what does that have to do with like extraterrestrial intelligence? Well, if intelligences outside Earth exist, which if they do, where is everybody? Space is a big place, right? But let's assume that we did assume for sake of argument, there is something out there, and it would send us a radio signal, and it thinks something like us. Then a message from them, a long enough message from them, would basically follow this law, where there would be some signals that occur more often than others. And then the next one occurs about half as often, and so on and so forth, right? Basically, it's a way to tell, oh, is this a radio signal, or is this just random gibberish? One of my favorite short stories of horror is SETI does detect a message from outer space, and the message is, shut up, be quiet, or they'll find you. So that's one of my favorite short stories. Yeah, and in fact, if you study the signal systems for different samples, you'll see that this follows human communication, as well as bottlenose dolphins, humpback whales, and adult squirrel monkeys. Simpler communication, like chipmunks, don't quite have that law or that complexity in language. Okay, so let's go ahead and work on this. Calculate the top total usage percentage of the top 10 words in a list. Store this result in a variable called top 10. At the same time, calculate the percentage for bottom 10 words in the list and store that result in the bottom 10. Okay, so what is it saying? Well, we saw that what we saw from Wikipedia that it says that the Brown corpus, whatever that is, said that the alone occurred for 7.5% of the usages. So we want to find out what is the usage of the first 10, right? What percentage does the top 10 just add up to, right? Now, how do we do that? So what we want to do in order to solve this problem is we need to find out what the sum of the frequency of the top 10 is, okay? So find sum of frequency of top 10. That's the first step. Then we also have to find the sum of the frequency of all words. In other words, right, if we wanted to know what percentage the percentage that the accounts for, right? We said it accounts for 220 million instances, okay? So if we wanted to find out what the percentage of that was, we'd want to say 220 million out of what? Out of the sum of all these, right? Out of the sum of all these, okay? So it'd be how many times the occurs divided by how many times everything occurs, and that will give you the percentage, okay? So if we want to find the top 10, we find the sum of all those top 10 words, find the sum of the frequency of all words, divide print, right? And that's what we have to do for that. So I will give you about 5-10 minutes to work on this. Feel free to work with other people. And then what I'll be doing after that is that I will be doing what I do every semester, which is going to the previous semester and copying, pasting from so that you can see how the graphing aspects of this work. So, because it's one thing to calculate these things, but it's another thing to visually see what goes on. And so I'm going to show you how we can visually see it go on. So take about 10 minutes to work on this by yourself. And, well, not by yourself. Feel free to talk to the people around you, please. Be social, ask for help. And again, we'll just come back and I'll give you the solution to this, which it just did. So it's 2:48 now, great. So how am I going to do this? So first off, as we've noticed, this has some, it wants us to do top 10 and top bottom. It's actually going to check our code. So let's go ahead and just quelch what errors we can. 0, we're going to need this, and bottom 10, we're going to need this. We're going to need these both at some point, and then great, now it's testing it and we're failing. And what we're going to discover is that the top 10 words make up 27.5% of basically the English language. The top 10 words basically make up a quarter of all the words we use. It's kind of astounding. All right, so how do we go about calculating that, right? So first thing I'm going to need to do is I'm going to need to open this file, which is words5000.csv, right? Words5000.csv. I mean, I could copy and paste from what I have above, but I'm just not gonna, because I only need the frequency for this. So let's go ahead and do that. So freq, that will be the frequency. I can ignore the rest of them, and then I need this to be data. I mean, it could be whatever I want. And I'm going to do lines is equal to data.readLines, so I can get everything. And then I'm going to, if I remember, the file, and if we remember, this file over here at the top, oops, it has the legend as part of the file. I don't need that legend, so I'm going to toss it out, right? I don't want to accidentally interpret that legend as data. And 0, 1, 2, 3. So let's toss out that beginning line, just like we did in the other one. So notice that I'm basically doing the same thing we did over here. I'm skipping everything but the frequency, because that's the only bit I care about for this problem. Okay. For line, I'll do L this time. For L in lines, for each L in lines, what do we want to do? We want to so this basically goes through each line one at a time and says, okay, for each of these lines, I want to know what the frequency is. So L dot split in order to split it up. Right? Because each line looks like this. So print, I'm going to go ahead and do this. Print L dot split. You can, print multiple stuff over here like this. So I'm just going to show you like what the before after effect is, right? For me doing it like this. Okay. Before and after. Oh, was never closed. What did I miss? Oh, the print. I missed the print. See, I make mistakes like that too. So we get this. Basically, we read each line, like one, the, a, and the split turns it into a list that looks like this. Make sense to everybody? That's what we're doing. This is very, very, so in case you need some incentive, something like this will be on exam 2. Okay, where I'm going to give you a file and I'm going to basically say, what are things I've done? Here's a file. Here's a file of numbers. Each line has 5 numbers on them separated by commas. Give me the sum of all even numbers in the file. Or write a program that would give me the sum of all the even numbers in the file. Right? So that's the kind of question I would ask. Right? So here, I just need to extract a number though. Let's go with so freq dot append to add something to a list. L, so we have the rank, the word, the part of speech, and at index 3 we have the number. So freq.append, actually why don't we go ahead and get that? I'm going to call it F for the frequency. Freq is equal to L dot, sorry, not L dot, but L3, the third thing in the list. And we're going to go ahead and turn that into an int. Freq.append F. Okay. And there we go. Now we've got our frequency list. Now, I'm going to use some clever solutions here to make this really short for me. I need the sum of the top 10 numbers. Well, fortunately, it's already been sorted for me. So the top 10 frequencies are the first 10 things in the list. So all I need to do is just slice the first 10 things, do a slice to get the first 10 things in the list. So I can do frequency, right? Here's frequency. The first 10 things in the list is 0 up to, but not including the 10th item, right? So this is indexes 0 through 9, right? So that's now a list of 10 numbers. Now I just need to add them together. And there's a nice keyword to add them all together all at once. Right? I could do a running sum, but at this point we've done that a million times, so might as well just take advantage of this, the sum function, right? Mentioned that a few times. Okay, the sum is one way to do that. And so now if I go ahead and run this, let's go ahead and comment out this print statement because we don't need it anymore. Fail. Oh, what did I miss? Well, there's all the values that I've added up, right? So maybe it was 22 million, not 220 million. Okay. It's so hard to read large numbers when you don't have commas. So anyway, there's our frequency. So now we have to figure out what proportion that is. And so we just simply divide that by the sum of all the numbers. So the sum of the first 10 numbers divided by the sum of all the numbers, including the first 10. And that will tell us what percentage that makes it. Which it says, it's a pass. It's about, let's say, 27.5%, because that flows a bit better than saying, oh, it's 27.6%, right? Sometimes it's okay to round like that for just simply being a bit more smooth in your language. Now for the bottom 10, we basically do the same thing. We need to get the last 10 things in the list. Okay, how do I do that? Well, what I do is, this is the first 10 things. And we know there's 5,000 things in this list, so we could do something like, from 4,991, but that kind of math I don't like doing that, right? Instead, what we're going to do is we're going to use negative indexes, okay? -1 is the last thing so we know that the bottom things in the list are the last 10 items in the list. -1 gets me the last item. -2 gives me the second to last. So here I can just simply go -10 to the end to say from the 10th to the last thing to the end. Make sense to everybody? Okay. Similarly, I could have just done it like this for this first one and not specified the starting point. And so there we go. The last 10, so let's go ahead and look at that over here. Just kind of by comparison to sanity check both the test and us, which is good. You always want to sanity check the tests in any real world application. Okay? Over here, we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these words are the, be, and, of, in, to, have, to, it. Okay? And think of other languages you may be familiar with, right? If you're taking Japanese, for example, think about how many sentences end with des, right? Which is essentially be, right? Or am, or some variation of that, right? Think about in any other language basically the word for saying the word that basically says this thing exists or this is an attribute this person has. That's a very common component in languages. Okay? And you'll be like, oh yeah, that word does get used a lot in my language. Okay? On the other hand, what's going to be less often in language is actually going to be pretty dependent on the language. I actually heard some people talking about, there was somebody talking as I was passing into the class, and they were and somebody brought up, why is color or how is color a thing? How did describing it come up? And actually, as it turns out, the color is a function of language more than anything else. Yes, we detect the electromagnetic, the radiation, the visible light that we get. Okay. And that's a small spectrum of the electromagnetic spectrum, right? But the words we use to describe that are actually, it's very interesting. It's a linguistical evolution. You get basically words for light and dark, and then red. And then maybe you start getting stuff like blue or green. And maybe you get a variation between them. And so so as languages progress, they pick up these words. It's actually a very interesting kind of aspect of language of what colors are. And you can even see this with just on Facebook sometimes where somebody will throw a random test online and say, is this color a green or a blue? And it's a tealish kind of color, right? There's some websites that actually rank, that make you classify some shades and say, hey, are these things? So anyway, language is very fascinating. So we were dealing with millions of frequency, but as we get down to these words, these last 10, we get censor, laundry, manual, pistol, naval, plaintiff, kid, middle class, apology, and till. And we see actually a fairly low over here, 0.88 on the plaintiff, right? Because you would typically get that in legal writing or news stories, but you're not going to get that in everything like the word the. Certainly not going to get it in children's literature unless it's very odd children's literature. Right, that's what that dispersion means. But here we're in the thousands for the word count. These are not nearly as common. Dictate, selected, kneel, harvest, nationwide, praise, bronze. These are not as common as other ones. So we see that. Now, before I graph it, there is one other thing I want to mention. This author, the author of XKCD, the guy who's got these random comics that he's been pulling up from, he did a book called Thing Explainer, which it was a book trying to explain science concepts using only the 1,000 most common words. For instance, here's a comic that he tried with that. Upgoer 5, the U.S. space team's Upgoer 5, the only flying space car that's taken anyone to another world, explained using the 1,000 words people use the most often. More skybag air for burning, cold plus wet. Part that falls off second. Lots of fire comes out here. This end should point towards the ground if you want to go to space. If it starts pointing towards space, you are having a big problem, and you will not go to space today. So, it's a very interesting linguistical exercise to try to explain things using a very limited vocabulary. It's a lot of. I'm not going to necessarily say it's fun because not everybody's going to find it fun, but it is intellectually stimulating. Okay? So now we can graph this. We can graph this data that we got from the word frequencies, and we're going to do so. So here's the code to do that. To do that, we're going to use a library called Altair, and what that is there's a lot of different graphing libraries in Python. I'm a big fan of Matplotlib, but I guess Altair just simply embeds in the web better, so that's why he uses that. So for this looks familiar, right? Open, CSV, and we've got rank, word, fart, frequency, where we basically add all those things in. And so we read the lines, we split them up, we add them into everything, okay? Over here, what I'm going to do, though, is I'm going to comment this part out and simply, ignore the math.logs. We'll get into that in a second. And don't be freaked out about logarithms. I'm going to go over what the heck a logarithm actually is in a second, because your teachers all taught it to you wrong, unless the new math the Common Core curriculum actually does a good job, in which case it does do a good job in a lot of places. But logarithms are still a mess for most things. So here what we do is that I just simply add all these on, okay? Then data is equal to altair.data. So this is the graphing bit. It says, here's the data I want to graph. I want to graph the rank of the word, so 0 through 5,000, as the x-axis. And the y-axis is going to be the frequencies we've done so. The equal sign over here, well, this is what I want to call that internally in Altair, and this is what I want to call the frequency internally in Altair, okay? Then make a chart out of this data. I want it to use a line, and I want you to draw a line between where x is the ranking and y is the frequency, and then display it. I have shared this code with you, by the way, so if you reload the page, actually, you'll be able to see it on your laptop. You'll be able to hit the reload button over here to just reload it, and it should say, hey, this was shared by your professor. And if you go to the code history, it will say, hey, this was shared by your professor. Now, Altair was used in some earlier exercises we didn't do. Altair. And it's pretty good, and it's pretty nice at what it does. Come on. Okay. And so I'm going to go ahead and run it. And let me just see. Oh, right. Let me go ahead and actually, what you'll want to do first is comment out this line and comment in this line. Comment out the line with the logs. I forgot to run it and then share it, whatever. Import math. Math was used, but not the, yeah, I get it. Okay, it's saying, and here's a graph. Here's our graph. So here's our ranking, word 0 to 4,000, right? And here's the frequency of the words. And it looks like there's not really a graph here, right? But I swear there is, right? If you see, this area is blue, and then it just kind of shoots down to close to 0, and then goes across, right? This is a useless graph. It's useless, utterly useless, right? Support is SVG. Can I do? Let's see. Does this help me at all? Because if it's an SVG, I can zoom in ostensibly. Yeah, so you can see it right there, the little jaggedness of it. That jaggedness is, of course, because the word frequencies don't precisely line up or don't really make a very nice line for us. So this is a useless thing. Instead, what we're going to do is we're going to do a log graph, okay? And typically, we like it. We get really excited when log graphs can kind of be turned into a straight line, showing that there's a kind of proportionality to this. Now, what the heck is a logarithm anyway? You probably learned at some point in high school or in college algebra that a logarithm is this inverse relationship for exponentiation, right? It's nonsense. I mean, that's what it is definitionally, but that's useless for a human. We aren't math machines, we're human machines, right? We're humans. We do human things. We like to count maybe to 10 maybe, and beyond that, let's let a machine do that, right? So what the heck is a logarithm, practically speaking? A logarithm tells you how many times you can split something up, where the base is what you're splitting it up into. What do I mean by that? So log base 10 of 100 is 2. Why? Because I can take 100 apples and split them into 10 piles of 10. And then I can take each of those 10 piles of 10 and split them up again. I am able to do 2 splits. That's why it's log base 2. Similarly, log base 2, so let's go ahead and look at log base 2 of 64. Log base 2 of 64, I can take log base 2 means just splitting it in half. So log base 2 asks, how many times can I split something in half? 64 can be split into 32. 32 can be split into 16. 16 can be split into 8. 8 can be split into 4. 4 can be split into 2. 2 can be split into 1. 1 can't be split. It's 6. And if I work up from there, I know from 6, log base 2 of 128 would be 7. Log base 2 would be of 256. So I know I'm right because I've got log base 2 of 256 memorized. Why? Because 2 to the 8th power is 256. You got to know that you will know that if you learn binary, because that's a byte. Sorry. But point being is that logs describe how many times you can split something. A log base 2 says how many times can I split it in half. Log base 3, how many times can I split it in thirds. Log base 10, how many times can I split this into tenths. That's it. There you go. Logarithms have been demystified. Now, of course, this doesn't really help you too much if I ask you, well, what's log base 10 of 500? But now you can know, well, it's between 2 and 3, because if I had 100 things, I could split it into twos. I could split twice. If I had 1,000 things, I could split it into, 3. but it helps, right? It helps kind of demystify this. It gives us a practical application. And in fact, that is the application we use a lot of the time. Now, it also just allows us, in this case, to also see just how dominant things are. So what I'm going to do here instead, for when I'm appending the frequency, what I'm going to do is I'm going to throw it into the math.log function over here. That's what that does. And that says I'm going to take this and I'm going to put it into, I'm going to put it into log function and give me the logarithm base 10 of it. Split it into tenths. Ask me how many times I can split it into tenths. Why? Because because now the graph basically becomes how many zeros does this number have at the end of it? That's another way of interpreting log base 10. How many zeros does this number have in it? How many did? Save and run. And then when we run this, we get this graph, which actually is kind of meaningful because it says, hey, so a lot of the words, right? The most dominant words we saw, the ones that make up a huge amount of the percentage of the language, they live here. And they have around 7 digits to 6 digits. And the rest of the words, they're kind of living here around the 4-digit range. 4 zeros range. So 8 digits, 5 digits over here, because that's how many zeros would be after the 1. So these words, and then over here we see on the end how we were getting into the thousands. There you go. So this allows us to kind of see this curve here, and that's really nice. And then we could also do the log of the rank, it says. So let's take a look at that one. I feel like that's less useful. But when you log both the x and y, we get this straight line. Or, well, not straight line. If you squint at it, it's straight, right? It's a bit of a crooked line, but we see this linear relationship between the logs. And that's what happens when you take any of those wacky graphs where we have something that looks like this and throw both sides into a log. And we see basically that we get this kind of halvening. And what this is saying is that there's this kind of halvening effect going on almost at multiple steps, where basically the first couple of things dominate, and then the rest aren't that frequent, comparatively speaking. But it's also a lot easier. Now, why do we care about this? Because this format's a lot easier for us to see. It's the same reason why when we rank things using like the Richter scale, which is used for earthquakes, we rank it in Richter 8, Richter 7. It's a 10-point scale, right? I believe. And the thing is that each of these is the power of and each. So the difference between a Richter 7 on the Richter scale and a 6 on the Richter scale is the 7's 10 more times powerful than the 6. The 6 is 10 more times powerful, more powerful than the 5. It's a power of 10 relationship. Why? Because it's easy for me to intuit that, okay, on a 10-point scale, how bad is it, right? From not too bad, you won't even notice it, to you're going to die, on that scale. It's a useful scale. But like trying to rank it between like on a range of 0 to 10 billion, where is this? That's not nearly as useful, right? Right? And then you'd have to remember, what's the difference between a 1 million and a 10 million on the Richter scale? That's not useful. That's why so that's kind of the use of it, to be basically. When we make the numbers easier for humans to digest, notice this is 0 to 8, where each number is a power of 10 more. This becomes a lot easier for us to look and see, okay, so over here these are fairly common. These are really common, but these are fairly common. And over here we've got basically nothing going on. So anyway, this is part of what data science is, and only really a small part. Being able to look at the data, analyze it, and interpret it. It's also a part of computer science, because we do all this data gathering, and being able to figure out how do we display these things, this is a very computer science kind of job as well. The lines between computer science and data science and IST are all very blurry in my opinion. So anyway, with that we are at 3:15. So on Thursday, this tail doves nicely to what we're going to do on Thursday. On Thursday, I'm going to go over dictionaries. And dictionaries, one of the things we can use them to do, one of the things we can use dictionaries for that you can't use lists for is we can do a word frequency count. In other words, we can build a data set like this using dictionaries. All right, take care. I hope everything's going well for you.